All right, so hi everybody. So last time we introduced the idea of electric current and Ohm's law and so on, and we talked about the real sort of fundamental reasons behind the ideas of electric current and so on. And so today what I want to do is to apply these ideas to some very, very simple circuits, some electrical circuits, specifically DC circuits, which means hooking things up to batteries. And so this is a direct current, meaning that the current just flows along nice and steady. There's no alternating current. We'll talk about that later on. We might allow for things like switches so that the current does change with time, but when it changes, it's going to be a nice steady buildup, and then it just continues on nice and steady from a battery. Okay? And so that's the difference between direct current and alternating current. And in fact, that's about the only difference. It turns out that direct and alternating currents are very, very similar to each other. You just change the math up a little bit. But again, AC comes in later because there's extra little complications that the changing electric fields and changing voltages produce. And we got to talk about those later on. Okay? And so today what I want to do is review some of the ideas that we discussed before from direct current, from regular current, and then apply those things. And specifically, there's a couple of very, very important laws and rules that come from looking at circuits, what are called the Kirchhoff rules. And so I want to try to work those out, having to do with what happens when you have circuits, okay, very general rules, following from very deep principles, and we'll talk about those. And then I want to talk about resistors and capacitors and different ways that you can hook them up and draw some basic circuit diagrams. Okay? We're not going to go too far into circuits. We'll get the ideas, but those of you who need to know much more about circuits, you'll take your electrical engineering classes and so on. You'll see those in much more detail there. Here, we're just getting some of the ideas, okay? And in the next lecture, I plan to do a little bit more sophisticated examples, but again, not so much more sophisticated, just because we're not going to need it for this class, and it's more about the real fundamental principles behind where these laws come from for circuits, not so much how do you apply them in scary-looking circuit diagrams, okay? And so, to get started, last time we introduced the idea of electric current. Okay. An electric current we defined as this I, and this is just very, very simple, the change in charge with respect to time. It's how your charge changes. If you got some blob of charge over here, and then it moves that same blob of charge over here, Q at T1 and Q at T2, then in order for the charge to get from one spot to this other spot, there had to be a current flowing. Okay, the current had to take the charge from this area to that area over there. Okay, and that's all it is. And so if your change in charge is dq, and it took you a time dt in order to produce that change in charge, then that's what your current is. Okay, and the units of current are just coulombs per second, and so that's called an amp. Okay? And so you measure so many amps for the electrical current. Okay, so a very, very simple sort of thing. And again, we said that the electric current is really electrons which are flowing, say, from the negative terminal of a battery to the positive terminal of a battery, but that was completely equivalent to imagining that there's positive electrons flowing from the positive terminal of a battery to the negative terminal of a battery. The sign of the charge doesn't really make any difference when you're talking about the flow of current. So even though it's really negative electrons flowing one way, we imagine it as positive electrons flowing back the opposite way. And oftentimes if you get minus signs or something like that when you work out the current, that means you just guessed the wrong direction. Okay, I'll explain a little bit about what I mean later on. So we worked out all kinds of very nice expressions for the current in wires in terms of mean time between collisions and number densities and all that kind of stuff. But I'm not so interested in that so much. I'm much more interested in just sort of simple ideas about the flow of electric current, kind of like the flow with water through a pipe. And water is kind of a good analogy. Okay? And so in addition to this, we talked also about things like resistors last time. And we have also previously talked about capacitors. And I'll remind you about those. And then also, we talked about batteries, okay? in sort of very, very simple terms. Okay, and I want to tell you just a little bit more about these kinds of things. Okay, specifically a resistor. An example of a resistor is anything that doesn't let current flow through it perfectly. Anything that has a resistance to the flow of electric current. And even perfect metals have some amount of resistance to flow. And what that comes from is the electrons sort of bouncing around. Okay, we talked about this last time. Okay, you picture the atoms as being this nice little chain of things moving along. And the electron, as it tries to travel through there, bounces around from place to place. And you only have this sort of net drift velocity when you apply a voltage across this piece of metal. Okay, so by applying a voltage, I mean you hook it up to a battery, and the battery induces a current that flows through that wire by creating an electric field from that battery, and then the charges respond to that. Okay, and so the resistance comes from the fact that these electrons are sort of bouncing around place to place. Okay, that's not 100% accurate. What it really is if you had a perfect atom, a perfect crystal of perfect, absolutely perfect atoms, where every atom is just the same as every other atom, then in this case, the electrons would flow along with no resistance, with no loss. They flow along almost as perfectly as if they were flowing through empty space. Essentially what happens is it kind of feels like they're a little more massive in this case. Okay? If you had one atom to the next, to the next, to the next being exactly the same, then that means that you have a perfect symmetry. Okay? You have this translation symmetry, a discrete translation symmetry, but you have a translation symmetry nonetheless. And if that's the case, if this atom here is exactly the same as the next atom, there's no reason for an electron to scatter off of one atom versus the next, and so on. And so that idea of symmetry tells you that you have a nice, constantly flowing bit of electrons, bit of electric charge. And so then where does the resistance come from? It comes from impurities in here. It comes from the fact that every once in a while you get some random junk like carbon or oxygen or whatever else sitting in there. And now this breaks the symmetry. And as soon as you've got an electron which is going from one atom to the next, well, different things can happen. When the electron kind of gets to this atom, sometimes it gets through, sometimes it gets reflected back or deflected at some other angle. So it's really the impurities in the metal that create the effects of resistance. And if you could imagine getting a perfect material, which is essentially impossible, but if you could get a perfect material, then it would have as low a resistance as possible. Okay? And this is different than superconductors. Superconductors are materials that, you try to make them as perfect as possible, but these are materials in which the temperature has gotten so low, the thermal motions are as low as possible, and quantum mechanics takes over, and these give you a situation in which the current flows with no resistance whatsoever. And the reason for this has to do with quantum mechanics and what's called the Pauli exclusion principle and spin and all kinds of complicated things, to which I refer you to Physics 103 for more information on that. Okay? For us, we think about resistors, and the examples of resistors are things in which, since the current doesn't flow perfectly, some of the energy of the voltage, some of the energy being supplied by the battery gets lost by the random sort of collisions here, which jiggle the atoms around. They pick up a temperature, and so the atoms, the metal itself gets hot, and at some point it gets hot enough to glow in many cases. And so one example would be a light bulb, an incandescent light bulb. Okay? Not an LED, those are a little bit different and so on, but a regular old light bulb, or an electric burner, a toaster oven, a hairdryer, anything like that. Heck, even a regular piece of metal can will warm up if you have a current passing through it. Okay, and so these are examples of resistors. Okay? Now, in circuits, you often want to use resistors to drop your current, to adjust the amount of current you get in different circuits so that you can do different, run different, whatever it is you're trying to run different loads and so on. And so if you open up a circuit, look at a circuit board and so on, you might see these sorts of little things here. These are resistors. Okay? These are actual what resistors would look like. And the little bands on these things tell you something about what the resistance is. Okay? They tell you the numbers and so on. And again, I'm not so worried about this. Again, those of you who are going to need this will learn about it in your electrical engineering courses and so on. But this is kind of what these things are. And what these things do is to tell you how much resistance do you actually have in there. Because remember, the current in a circuit is inversely proportional to the resistance in that circuit. More resistance drops the current. So if you only want so much current, you choose a certain amount of resistance in your circuit. Okay? And so these are examples of these resistors. Okay? And again, the numbers here, the colors here represent something, and by looking at this, when you get good at it, which I'm not, okay, you can look at this thing and say, oh, I know what this what this resistor is, and so on. Okay? And so these are resistors. Okay? Again, basic circuit elements. Okay, one of the three basic circuit elements we're going to talk about today. Okay, another thing would be capacitors. Okay, and capacitors. Okay, and you remember the flux capacitor, which makes no sense whatsoever because flux is something passing through. Capacitors are storing things up. Okay, these are your capacitors that you might see in circuit boards, different amounts of capacitance. And remember, capacitance is, well, I'll talk about the units later. Okay. Remember, a capacitor, one example of it was these couple of parallel plates connected by a wire where you have some positive Q on one plate and some negative Q on the other plate so that there's a voltage between the two. Okay, there's some delta V. And that delta V is equal to Q times over C. Okay, where C is the capacitance. And in the case of a parallel plate capacitor, this was epsilon naught A over D. But we also discussed other situations in which the capacitance was different. In fact, this is really the way that you define capacitance. We talked about the cylindrical capacitor and so on. Okay, and so again, capacitors were useful for storing up charges very high and then discharging them very quickly. We're going to see later on, probably next time, the next lecture, that capacitors are very much like batteries that drain away very, very rapidly. All right, so those are capacitors. Okay, the last element I want to talk about is a battery. Okay, and you got regular batteries. You could also have microverse batteries for Rick and Morty fans. But I'll look at regular batteries that aren't being supplied energy by people stomping on pedals. In the case of regular batteries, you got chemical reactions which are going on, which frees up charges, and those charges move around, and they provide the difference in voltage. That charges separate into different spots, and so you get a voltage on your battery. Okay, and that's what it is. It's a voltage supply, and the voltage on the battery, okay, between the positive and negative terminal, delta V battery, is usually written in this scripty E, or a Russian yeah, if you sort of like that. And why this is, it goes back to an old-fashioned way of thinking about what batteries' voltages are, what voltages were, in fact. It goes back to what's called an EMF, an electromotive force. And so people used to think that there was some kind of force that was pushing the charges around in there. And of course you know that there is, but there is because there's an electric field created by this battery. And that electric field produces an electric force on the charges. But they didn't understand it at the time in these terms. And so this sort of EMF as a voltage, remember a voltage is not a force, it's a charge, it's a energy per unit charge, but the name kind of stuck. And so the voltage on the battery is this E. In the case of AA batteries, okay, your E is 1.5 volts. In the case of a 9-volt battery, okay, you figure out how much voltage is on a 9-volt battery. Okay? And so this is something which is given. And we're going to imagine that whatever circuits we hook up to this thing, we don't hook them up so long that the battery dies. Okay? We're going to hook these things up so that E is taken to be constant. Okay? At least over the lifetime of the experiment that we do. Right? And so these are the basic 3 circuit elements we're going to start with today. Now, of course, there's all kinds of other circuit elements. There's transistors, there's amplifiers, and so on. There's inductors, which we will talk about later on. But again, we're not going to get too fancy with all of this kind of stuff. We're going to keep things very simple. Okay? So now, I want to start thinking about actually making circuits. In other words, hooking up batteries to light bulbs and figuring out how much current is there, how much power gets burned through those light bulbs, and so on and so forth. And to do this, I need to start thinking about ways of drawing these things, because it's fine to just draw random pictures and so on. Okay, so that if I want a battery okay, with the positive terminal here and the negative terminal here hooked up to a light bulb. Well, that's one way of doing it, but that doesn't look very nice. Okay, that doesn't look very sort of technical and blueprinty and engineering nice. And so instead what I'm going to do is introduce some nice symbols for these things. Okay, so for the battery, okay, the way I'm going to draw this battery is I'm going to imagine that the wires here come in and it goes to a little small thing and it goes to a big thing. Okay, and this big thing here is going to represent the positive terminal, and this other side over here is going to represent the negative terminal. And then I imagine that the positive terminal pushes positive charges out of there, and the current flows through the wire from positive back to negative. That's the thing I'm going to do for the battery. Okay, I'll show you these things in a minute, and I'll also show you other notations for this. Okay, I'm just showing you the ones that I want. For a resistor, okay, I want something where when I think about it, I'm imagining something resistive, something like friction, something that doesn't look like it would be nice for the current to pass through. And so for my light bulb, I'm going to draw it with this jagged line. Okay? And it's got a certain resistance here, and this thing here has got a certain voltage. Okay? That's my resistor. And remember, the resistance is measured in ohms. Okay? And this E is measured in volts. And then finally for a capacitor, well, again, you remember what a capacitor was. It was two parallel plates separated by some charge. Well, I might as well use my two parallel plates separated by some charge. Okay? With some capacitance C, and remember, capacitance was in farads. And since Q equals CV, a farad is a coulomb per volt. Okay? And an ohm, since V equals IR, an ohm is a volt per amp. Okay? So again, I'm going to redraw these all in a second, but these are going to be my basic circuit elements. Okay? And so I've got them here. Okay? People have chosen different ways of representing these things and still choose different ways of representing things. But I'm kind of going to stick with these ones. Okay? So resistors are sometimes written that way, but again, I'm going to do it as this jagged line. That's my resistor. Okay. In my capacitor, okay, again, some people, the old-fashioned ones, draw it with kind of a curved line. For my capacitor, I'm going to draw it as two parallel lines. Okay. And then for my battery, some people draw it doubled up like this. I'm just going to stick with this one. Okay. So here's this positive terminal there, negative terminal there, or whichever way you've got it. Notice capacitors and batteries look very similar, except capacitors have both the same length, batteries have different length. Okay? And just to remind you what the change in voltage was across these things, okay? The change in voltage from Ohm's law, actually let me just put in a new slide. Okay? Ohm's law works for a resistor. That said, that if you have a resistor with some resistance R, and there's a current which goes across this resistor, then there's a drop in voltage between both sides of this resistor. And that drop in voltage, that change in voltage for this resistor, is I times R. Okay? And this is for a resistor. This is not for a capacitor. This is not for a battery or anything else. Okay? And so the voltage is higher on one side when the current is coming in than it is on the other side. And so there's a negative change in voltage through that resistor, which is minus I times R. The voltage drops when you move along the direction of the current. Again, we're going to talk about all this stuff in a little bit. But this is the magnitude of that voltage drop. Okay? In the case of a capacitor, okay, when you have this capacitor here, you put a certain amount of charge Q on here and a certain amount of negative charge negative Q on the other side when you got this capacitance. And as we've seen, the charge that you induce is delta V over times C. Q equals C delta V times C. And so the delta V across the capacitor is the charge on that capacitor. In fact, let me call it little q, because the charge might change as time goes on. divided by C. Okay, so this is for your capacitor. Okay? So, important things. And finally, for a battery, okay, well, that's nice. Okay, in the case of the battery, the delta V for a battery, well, that's just my E, and this is constant. Okay? So these are the things to keep in mind, and of course, the only other thing that you need to remember is that I is dq dt. Sometimes this will pop up as well. So these are the things that we can build everything else up from. One more thing that's handy to remember is the power, okay, in a circuit element. Okay, by circuit element, I mean a resistor, a capacitor, a battery, okay, is just P is equal to I times delta V, where delta V is the current, is the change in voltage across that circuit element, and I is the current. So for instance, for a resistor, okay, just change up colors here. Okay, P resistor equals I times delta V resistor, and that would be I times I squared R. Okay, I times IR because V equals IR. For a capacitor, okay, P for the capacitor is the current times delta V capacitor, and that would be I times Q over C. Okay, again, I should probably stick with little q here. Little q over C. And then finally for a battery, the power supplied by the battery would be I times E. Okay, and that's kind of as much as you can do. Right? So there's different things that you can figure out from here. For instance, you can figure out how much energy is being supplied by the to the capacitor, how much energy the capacitor has stored up. Okay? How? Well, if you know that this is d energy dt, you can integrate both sides of this. I don't want to go over that now. I think I'll go over that in the next lecture, at the beginning of the next lecture, when we start to see slightly more fancy stuff, or sometime during the next lecture. Okay? I hope I remember. So, that's it. Okay? And so now, with these circuit elements, I can start thinking about simple circuits, and I can build things up from here. So here's a simple circuit. Okay? This represents a battery connected to a resistor. Okay? In other words, it's a flashlight. Okay? It's a flashlight where here is your battery voltage, here is your resistance R. Okay? And in order to start figuring out things like what is the current through here and so on, I got to understand something about how current flows, and about different properties and so on. Okay? And these different ideas are encapsulated in what's called the Kirchhoff's laws. And so I want to talk about these now. Okay? And these laws are very, very, very simple, but they form the basis for circuits, okay? Both direct current circuits and alternating current circuits. And so I want to talk about these things now and talk about where these laws really come from, the fundamental reasons for these. Okay? So the first law is what's called the Kirchhoff loop rule. Okay? Sometimes you might hear it as other words, KVL, Kirchhoff voltage law or voltage rule or something like that. But we'll talk about it like this, and you can sort of translate it as you like. Here's the idea. Suppose you've got a source of voltage. Okay? And by source of voltage, I mean that this is something like a battery or a generator or something like that in AC. So this is completely general. And this is hooked up to a load. Okay? And by load, I mean that this might be a bunch of resistors, bunch of light bulbs, capacitors, whatever it is you want. Okay? And these things are carried along by the wires. And so there's some current that flows in, and there's some current that flows out of that load. And so you've got a certain amount of voltage which is being supplied here. Okay? You've got a delta V source. Okay? In this case here, okay, the load is using up some of this voltage. Remember, voltage is very much like energy. Okay? The energy of your charges is the charge times their change in voltage. So every time you send charges, every time your electrons move through this source, they bump up their energy by the charge on the electron times delta V source. So they bump up their energy. Now, so they leave the voltage source over here with more energy than they had when they came in. Okay, so the battery is supplying your energy, okay, by supplying the voltage. Now, when that happens, they come back here to the load. And in the load, they've got to lose energy. Okay, lose energy. Why? Well, suppose that they just kept the same amount of energy going through the load, then they got back to the source. Well, they would pick up more energy and more energy and more energy and so on. Every time they went through the source, they'd pick up more and more and more energy. The circuit would melt. The whole thing would blow up. And so they got to lose energy. And in order to have sort of conservation of energy so that the thing doesn't sort of just stop running, the electrons don't lose all their motion, or they don't get more and more motion, whatever energy they gain from the voltage source has got to correspond exactly to the amount that they lose through the load. Okay, this is just conservation of energy. And so this says that if they gain an energy Q electron, delta Vs, then they have to lose an energy minus Q electron, delta V load. And for both of these things to be true, that tells you, for conservation of energy, for conservation of energy, this says that Q electron delta Vs has got to equal Q electron delta V load. Okay? The magnitude of these things. Canceling off the Q electron, this says that delta Vs minus delta V load is equal to 0. Okay? Now, I never said how many batteries you've got. I've never said how many light bulbs you've got. This thing is true in general. And so this is this idea, okay, can be generalized. Suppose that you have source 1, okay, here, and you got source 2 here, okay, and these things are connected. So 2 batteries, and then you got load 1, and then load 2, and then say load 3. Okay? And so the current gets pushed along in this direction, and you got 2 increases and 3 decreases. Okay? So if I think about these things, the total energy supplied should be Q electron times delta V source 1 plus Q electron delta V source 2. Okay? Both of these sources are providing an increase in the energy to the electrons which are going along in there. Okay? Total energy used should be Q electron delta V load 1 plus Q electron delta V load 2 plus Q electron delta V load 3. Okay? So again, if energy is going to be conserved, if your energy is going to be conserved, the total energy supplied, let's say E in, just to call it something, and E out is the energy used, E in has got to equal E out. Now, obviously, you can generalize this to more cases, and this is where we get the Kirchhoff loop rule. Okay. Here's the idea. Suppose that you have a circuit, closed circuit, okay? And it's got to be a closed circuit, otherwise the current just doesn't flow, okay? If you have a break in your circuit here, okay, where this thing, instead of having a closed thing, it just stops like that, current doesn't flow anymore, okay? It just kind of bunches up here and then starts pushing charges back the other way. So the current flows unless you have a nice closed circuit, okay? So for a closed circuit, for a closed loop, okay, what happens? Okay. Suppose that you go around that loop. okay, in the direction of current flow. And we're going to see examples of this as we go on. Okay? In the direction of current flow. Add up all the changes in voltage around that loop. Okay? In other words, I go around this loop here. Okay? I get an increase. Going along the wire doesn't change the voltage. You say, isn't there some resistance there? Yeah, but that resistance in the wire is going to be small compared to whatever it is we have in the load, sort of by design. So we ignore wires. Okay? The wires aren't going to provide very much of a change in voltage. Okay? And so I got two increases here. Voltage source 2, voltage source 1. Then I go through here. Well, this drops, and this drops the voltage. Why? It's using up energy. It's getting hot. It's giving off light. And so that uses energy. It's not supplying the energy anymore. Kirchhoff's law says, take that thing, okay, sum up the changes in voltages through the loop. Okay, I here stands for whichever one you've got. Kirchhoff's loop rule says you add all these things up. Okay, what do we get? Since these things have got to equal each other, okay, energy in equals energy out, this tells you that summing all these things up gives you 0. Okay, and this is true for any loop. Okay, any closed loop. Incidentally, this also holds in the case of alternating circuits. Okay? And again, where does this come from? This is conservation of energy. Okay, this is conservation of energy. The energy is going to be conserved as it flows around the loop. Otherwise, your circuit will just stop working, or otherwise your circuit will blow itself up. Okay? If you get more energy every time you go around a loop, it blows itself up. If you're losing energy the whole time and losing energy faster than you're replenishing it, the charges just stop moving. Okay? Or they would drift along at some constant velocity, bumping into each other, and eventually just stop. Okay? And so this is very important. Okay? And so this lets us figure out something very nice. Okay? So for instance, suppose that we have a simple circuit. Okay? Suppose I got a battery. So as an example of this, suppose I got my battery here, and I've got one resistor, and I've got another resistor tied to it. Okay? So suppose, just to make some easy numbers, this is 2 ohms, and this is, say, 3 ohms. And let's say that this is a 10-volt battery, just picking nice numbers. Okay? So I got 2 light bulbs hooked up to one battery. I want to know what's the current in the circuit. Okay? And so again, this is my resistor, R1, this is my R2. Okay? And this is my voltage on my battery. What's the current in the circuit? Okay? Well, to figure this out, I use Kirchhoff's law. Sum of the changes in voltages through the loop should be equal to 0. Okay? So what do? I pick a spot anywhere on the loop, anywhere you like. Okay? Here's a good spot. Okay? So I go around. I know that if this is the positive term and that's the negative, then the current moves around the loop in this direction. So I follow that direction. No change in voltage, it's just a wire. Then I get to the battery. So my first change in voltage through the loop, as I've chosen it, is a positive E. The battery, I'm moving in the direction of the current. The battery supplies some extra energy, and it supplies a voltage E. Now I come around, I get here, and I say, well, the voltage through here is going to drop, minus delta V through R1. Okay? Change in voltage through that first resistor, it's going to drop. Why? It's going to get hot. It's going to use up energy. And since I'm moving in the direction of current, it's going to be negative. Okay? Now there's no change, no change, no change. Now I get back to here. Now there's a change in voltage, delta R2. Okay? Then I get back to the same spot. That's equal to 0. So in other words, the battery voltage is delta V R1 plus delta V R2. Okay? So each of these light bulbs take up a certain amount of voltage, and that's being supplied by the battery. Now, if I want the current, okay, then I need to remember Ohm's law, that delta V through a resistor is I times R. And for reasons that I'm going to tell you about in a little bit, it turns out that the current is the same in a loop. If you're in a single loop, the current is always the same. Where does that come from? The other Kirchhoff law, which we'll get to. Okay? And so this thing here, if I know that I in R1 equals I in R2, why? We're getting there. Okay? Then this means that E should be equal to I times R1 plus R2. Okay? Because delta VR1 is just IR1, delta VR2 is just I times R2. And so, from here, my I is equal to E over R1 plus R2. And so that will be 10 divided by 5, 2 amps. That's the current in the circuit. See how it goes? Not so bad. We'll do other examples. Okay? And so, incidentally, these resistors are connected in what we call series. It's one after the next. And we'll talk about the rules for this in a little bit. Okay? So that's one of the Kirchhoff's rules. So again, if you have a single loop, then the sum of the changes in voltages around any loop, okay, doesn't matter what the loop is, that should be equal to 0. Okay? Then there's another one. Junction rule. Okay. Sometimes called the current rule or something like that. Here's the idea. Suppose you got a wire. Okay. If you're traveling along this wire, then the electrons just travel along nice and steady. You don't bunch these things up. Okay. They don't get stuck anywhere, because if they get kind of stuck anywhere, then they just kind of push each other apart. And so along a wire, the current is constant from place to place. Okay? The current can change with time. It can go up and can go down. It can oscillate like you have in AC circuits. But the current at this spot is exactly the same as the current in that spot, even if it fluctuates in time. And again, that's just because the charges don't get all bunched up. Okay? Whatever charge flows into some region flows right back out from that region. Okay, that's the idea. Now, suppose you got something a little more interesting. Suppose you have a situation in which you have a current coming in. I'm going to call it I1, and then you have a little junction. Okay? You splice two wires off of this. And so you've got some of the current going this way and some of the current going that way. And I'll call this I2 and I3. Okay? And so you're bringing in 10 amps, and then you split off two wires, and suppose that the current travels evenly. Both wires are identical. There's no reason for the current to travel one way versus the other way. And so you might guess that I1 should equal I2 plus I3. In other words, how much current you have going into the junction should be the same as the amount of current that you have going out of the junction. That's your intuition. And that's absolutely true. Okay, this is true. Okay? And so, where is this coming from? This comes from, again, the fact that if you have charges which are coming in, the charges don't get lost. The charges don't get stuck in the junction. And so whatever charge flows into this junction in a certain time has also got to flow out of that junction in the same amount of time. Okay? In that certain time. Why? Because again, they don't get stuck. Okay? They don't build up there. If any charges build up in this junction, it would just start pushing the charges out of that junction. And so, because of conservation of charge, okay, we get the junction rule. Okay? We get this junction rule. So charges are conserved. Okay? So you might wonder, what happens if I get a little fancier? Now suppose I have an I4 coming out. Well, then I1 should equal I2 plus I3 plus I4. What if I have another wire coming in, bringing in an I5? Well, I put it over here. The current coming in is the same as the current going out. And so, if I want to write it mathematically, some of the currents into a junction is the same as the currents out of a junction. And that's Kirchhoff's junction rule. Okay? And between this, which is a consequence of conservation of charge, and this, which is a consequence of conservation of energy, we have enough to do most any problem that we can think of. Okay? All right, so hopefully this makes sense. Very, very simple things. Okay? And so that's also how I knew that the current here was the same through both resistors. Because I only got one loop, because I'm not splicing off anywhere, that means that the current in this loop is completely the same. Okay? All right. So now what I want to do, okay, to get to do more fancy examples and things like that, I want to show you other ways of hooking things up. Okay? The simplest case would be just to hook things up kind of like this. Okay? Resistors hooked up and things like this. But you notice I can hook up a couple of resistors like this. One right after the next. Suppose that I've got a situation in which I need, say, a 10 ohm resistor. Okay? I just want my current to be such that I need a 10 ohm resistor, but I don't have a 10, but I have two 5s. Is there some way of hooking up those two 5 ohm resistors in such a way that it gives me the same effect as having a single 10 ohm resistor? Well, I think you can see from this problem, yeah. If I hook them up this way, notice that I've added up the resistances here. And so the 2 and the 3 ohm resistor, and this just follows from the loop rule plus the junction rule. In this case, the 2 and the 3 ohm resistors have gotten together, and this acts like a 10 over a 5. So this 2 and the 3 hooked up together in series acts very much like, in fact, it acts identically to a single resistor, which is equal to the sum of those resistances. Okay? And so if I hook up resistors in series, okay? In other words, I take one resistor, some R1, and some next R2. Okay? This is equivalent to having one single resistor, R equivalent. Okay? And you might guess that R equivalent should just be R1 plus R2. And if you add on a third one, it would be plus R3, and so on. This turns out to be right. Okay? How do you see that? Okay? Well, suppose that you imagine it like this. Suppose you imagine, here's your circuit. Okay? And here's some battery with some voltage E. And suppose let's take 3, because I already did 2, but let's take 3. Here's my R1, here's my R2, here's my R3. Okay? And this circuit here produces some current I. And I'm going to say that this circuit is equivalent to some other circuit with the same battery, but some R equivalent. Okay? Only a single R equivalent. Okay? What's that going to be? Well, let's see if I can figure out. Let's see if I can figure out the relationships. Not so hard in this case. From here, I know that from my loop rule, the change in voltage through this equivalent resistance is the same as the battery voltage. Okay? Whatever is supplied by the battery has got to be used up by this voltage. Okay? Delta V R equivalent. Okay? And this should be equal to I times R equivalent from Kirchhoff's laws. And so this tells me that E is I times R equivalent. Okay, nothing to it. All right. So that's that, for that equivalent circuit. And again, the whole idea is that I'm replacing this bunch of stuff here, this load here, by this load right there. Okay? And I have it so that I've chosen it so that it gives me the same current. Okay? It does the same job. Well, in this case, let me redraw it. Okay? In the first case, here's my battery. R1, R2, R3. From the loop rule, what do I have? Again, I pick a spot here, and that looks like a good spot. I move this way. Some of the changes in the voltages through the loop should be equal to 0. And so the first thing that I get going around, again, I know that the current is going to come out from the positive terminal to the negative terminal. Some of the changes in voltage, first thing I get is a plus E. Next thing I get is minus delta V R1. Okay? Then the next, delta V R2. The next, delta V R3. And when I get back to the same spot, this is equal to 0. So in other words, my E is delta V R1 plus delta V R2 plus delta V R3. But from Ohm's law, I know that delta V is equal to I times R. And also from the junction rule, I know the current is the same. The current is the same everywhere in this circuit. Why? I don't branch off. I don't have any junctions. So the current is the same. And so combining this and this is the same as I times R1 plus R2 plus R3. Okay, and that's my E. Okay. But remember, this is supposed to be equivalent to this circuit here. And this also, so this tells me that this same thing here should also be equal to the same E, the same I times the same R equivalent. Okay, why? Because I didn't change, when I changed my equivalent circuit, all I changed was the resistors. I didn't change the voltage from the battery, and I chose the equivalent resistance, so it does the same job as these three resistances. In other words, it gives me the same current. So by defining it in this way, these things are the same, and these are the same, so this tells me that my R equivalent is equal to R1 plus R2 plus R3. Okay? So this is resistors in series. Okay, so just to write it. Okay? And in series means one right after the next, all on the same wire. Are n of these things. This is equivalent to one R equivalent resistance, okay, where R equivalent is equal to R1 plus R2 plus Rn. So if you like, sum I equals 1 to n of R sub i's. Okay? So in other words, to get the equivalent resistance of resistors in series, you just add up the resistances. Okay? Piece of cake. Nothing to it. Okay? All right. So that's nice. That's not the only way you can hook it up, though. I keep saying if you have this junction, if you splice off of things. That's one way of doing it. What about resistors hooked up a different way? Okay, suppose that you have one resistor like this, R1, but then you have another one over here. Okay, this R2. In this case, these two things are not in series. You've branched off. The current is different in the different parts of the circuit. And so you've got resistors not in series. You've got resistors in parallel. Okay, they're parallel to each other. And I want to figure out, well, what happens in this case? Can I replace this circuit by another equivalent circuit? Okay. Yes, I can. But the rules are a little bit different. In fact, the rules are more complicated in this case. Okay? Let's see how we do it. Okay? So again, I'm going to draw the same sort of thing. I'm going to imagine some battery here, E, and this puts out some current, and this time I'm going to call it some I1. Actually, let me call it just I. And so here's my R1 and here's my R2. And when this current, well, hang on, here's the idea. This is going to be equivalent to the same battery, the same current, and the same R equivalent. Well, sorry, an equivalent R equivalent with the same current. Again, it's important. Same current, same voltage. The only thing I change is this combination of resistors. This thing just gets replaced by this thing. That's all. The E is the same, and the I is the same. Okay, so this one I've already solved. Okay, this one over here I've already solved. This tells me that E is equal to I R equivalent, which I'm going to write as I is E over R equivalent. Okay, I'm just going to solve for the current. Okay, the current in the circuit. Now I got to work out the other one here. Okay, this one's a little more work, but it's still not so bad. Let me redraw it. Here's my E. Here's my R1. Here's my R2. Now, this battery here produces some current I. Now, when this current gets to this junction here, it's going to split. And you're going to have some current I1 going this way and some other current I2 going in that direction. Okay? In such a way that I is equal to I1 plus I2. Okay? That's your Kirchhoff's junction rule. Okay? That's where this thing comes from. Now, what's the current in each of these circuits? Okay? How do I figure that out? Well, here's where the Kirchhoff's loop rule comes in handy. So I've got actually a total of 3 loops right now. Okay? Let me show you. Here's one loop. Okay? One loop, I can go around like this. That's loop 1. Okay? Another loop, so in other words, I just go from the battery through resistor 2. Actually, I guess I'll call this loop 2. Okay? Makes more sense if it's going through resistor 2. And I'm bypassing resistor 1. Okay? Here's another loop. I go through here. And here's my loop 1. Okay? I bypass resistor 2 and just go through resistor 1. Okay? What about my third loop? Where's that one? This one. Loop 3. Okay? Loop 3 doesn't even look at the battery. And so it just goes between I1 and I2. And so Kirchhoff's law says that for any of these loops, okay, loop 1, for any of these loops, the sum of the changes in voltages as I go around that loop has got to be equal to 0. So let's just, for practice, work out each one. Loop 1. Okay? Sum of the changes in voltages around the loop should be 0. Well, again, pick a spot. I'll start always in the same, well, no, I guess not. Let me pick this spot to start in, because that's the same for all 3 loops. So I go around in the direction of increasing current. So I go around, I go up, I get a positive E, then I go around, no change, minus the change in voltage through R1, but that's I1, R1. Okay? Not I, but it's I1. It's the current that's traveling through that resistor, and this should be equal to 0. Okay? Loop 2. Okay, sum of the change in voltage through the loop, delta VI. Okay, again, starting here, I go around the loop, I get to a positive E, minus, I skip R1, I go through R2, minus I2 R2. Okay, this is the change in voltage through R2, and that should be equal to 0. And so this tells me that E equals I1 R1, and E also equals I2 R2. So it's the same change in voltage. Does that make sense? Yes. Let's look at loop 3. Okay. Now I start here. I go up. Actually, let me start here. Okay, you'll see why in a second. So I start up here. I go around. Now I'm traveling with I2. Okay, I got minus I2 R2. I'm traveling in the direction of the current. I go along. Now I get to here. Now I go up. Now I go up. I get I1 R1, and that should be equal to 0. But I'm traveling in the wrong way. I'm going up where the current I1 comes down. That changes the sign. That changes the sign. Okay? So you spend a little time with this, you get the hang of it. We'll see other examples of this later on. But because in the case of I2, I'm moving in the direction of I2, then it's a drop in voltage here. But here, because I'm fighting it, the I is sort of in the wrong direction, and that gives me a plus here. And so this tells me I1 R1 equals I2 R2, which is exactly what you get here. They're all equal to the same battery voltage. Okay? So that's the idea. Okay, you see how it works? I hope. Okay? And so, from here, what can I figure out? Well, I know that I is equal to I1 plus I2. But from these expressions, okay, I1 is E over R1. and I2 is equal to E over R2. So that tells me that this is equal to E over R1 plus E over R2, which if you like is the same as E over 1 over R1 plus 1 over R2. Okay, so that's my current. Little different. It's not 1 over R1 plus R2, it's 1 over R1 plus 1 over R2. Now if I go back here and remember what my I also is in terms of my equivalent circuit, okay, I found that I was equal to E over R equivalent from this equivalent circuit back here. Okay? But now it's the same I, it's the same E, so this should also be equal to E 1 over R1 plus 1 over R2. And therefore, 1 over R equivalent is equal to 1 over R1 plus 1 over R2. And this is resistors in parallel. Okay. Please note, okay, let me write this. Okay, please note 1 over R equivalent equals 1 over R1 plus 1 over R2 is not the same as R equivalent equals R1 plus R2. These things don't flip over like this. I hope you can kind of catch that. I hope I don't have to say that. As a check, suppose R1 equals R2 equals 1. Suppose they're both 1 ohm resistors. That's a bad one. Suppose they're both 2 ohm resistors. So in parallel, okay, 1 over R equivalent equals 1 over 2 plus 1 over 2 equals 1 over 1. And so R equivalent is the inverse of that, is 1 ohm. So the equivalent resistance of resistors in parallel is smaller than the resistance individually. Okay? But in the case of in series, okay, R equivalent would be 2 plus 2 equals 4 ohms. Okay? And so that's in series. So your equivalent resistance is bigger when things are in series, and they're smaller when they are in parallel. All right? All right. So here's seeing these things. Okay? Here's how you might draw them out. And so in these situations here, in, say, series, remember, this is your series. Okay? And this is your parallel. Okay? In the case of series, there's a voltage drop across each of these things. Okay? In the case of series, you got a delta V R1, delta V R2, and so on. Okay? The current is the same across each of these resistors, but the voltage continues to change. The voltage is different. Whereas in parallel, current is different. Okay? But the voltage is the same. Okay? That's what the junction rules say. And these things here are just pictures that I found online of somebody using what's called a breadboard with the resistors to kind of show you an example of how these things actually look when they're hooked up this way. Okay? And so each of these little dots here are all connected to each other. Okay? So if you plug them in across these rows, there's a connection like this. Okay? Whereas the ones that run this way are not connected to each other. Okay? So it's only connected up and down versus side to side. Okay, so this is just examples of what these things look like. Okay, and so based on these things, you can always figure out simple circuits by sort of breaking things up and reducing them down to simple cases. Okay, and so in order to get a feel for this, I want to do a nice simple example here. Okay, of a couple of resistors. Okay, 4 resistors here hooked up. And I want to figure out some things like, well, what's the power through each resistor? Okay, what's the current in each resistor? And so on. Okay, so I've got this situation here such that I've got a 16-volt battery hooked up to this combination of resistors. Okay, where R1 and R4 are in series with each other, they're also in series with this parallel connection here of R2 and R3. And so what I want to do is I want to try to figure out, well, what's the current in each of these things and what's the power? And in order to do this, I just have to remember that delta V equals IR for a resistor, and that P is I squared times R for a resistor. Okay, it's different for other circuit elements like capacitors and so on, which we'll talk about in a little bit. Okay, so how do I do this? Okay, well, I can, look, I got 3 different loops here. I can work those things out. I can use the Kirchhoff laws and junction laws and things like that. For instance, I know that there's a certain current here, okay, call it I1. When it splits here, there's going to be some I2. There's going to be some I3. Okay? And you can work this out. In fact, I encourage you to try working this out in as many ways as you can because you get a better feel for it. Okay? In this case, there's a couple of simplifying tricks that we can do. Okay? I noticed that this thing here is parallel. Okay? These two things are connected in parallel. And so because of that, I'm going to redraw this circuit. I'm going to redraw my 16-volt circuit here with my same R1 here, my same R4 here, but some R equivalent here, where this equivalent resistance is what I get by replacing this combination of stuff, which is in parallel with an equivalent resistance. Okay? And so this equivalent resistance, because it's in parallel, I got that 1 over R equivalent is 1 over R2 plus 1 over R3. Okay, and just to plug in the numbers, 1 over 4 plus 1 over 4 is 1 over 2. And so this R equivalent here is 2 ohms, not 1/2, 2. Don't forget to flip it over. And so based on that, this circuit then can be written as another equivalent circuit, 16 volts. Okay, I hope you can read this. R equivalent, prime just means a different one. Now this collection here is in series, and so I just add up. I add up 2 plus 2 plus 4, that's 8 ohms. And so now that's nice. What does this tell me? This tells me that the current which is coming out of this battery is 2 amps. How did I know that? Well, just take V equals I times R. And so there's 2 amps which is coming out of this battery. So 2 amps coming out of here. But that 2 amps is the same as is traveling through R1, and it's the same as traveling through R4. Why? Because of the junction rule. At this point here, there's no junction. Okay? Whatever current is flowing out of the battery goes through R1 and R2. And so I can go ahead and write in the resistor at R1 has got 2 amps. The resistor at R2, I don't know yet. I don't know 3, but I do know 4. That's also 2 amps. Okay? Now, you can figure out, based on the fact that you know the change in voltage through each of these things, you can work it out. You can work out what the current I2 and I3 are, but we can be a little clever. I know that 2 amps flows into this point. Oops, sorry. 2 amps flows into that point right there. If R2 and R3 are exactly the same, there's no reason for more current to go through R2 than there is to go through R3. Since R2 and R3 are exactly the same, they got to split the current evenly. And so R2 gets 1 amp and R3 gets 1 amp. Okay? Now, if you didn't see that, you can work it out through the loop rules and the junction rules and so on. The change in voltage through R2 and R3 have got to be equal to each other. And so that will tell you what your currents are. Again, you try working it out all kinds of different ways. Now to get the power, it's easy. The power, we just take I squared times R. So 4 times, this should be 8 watts. Okay. I squared times R, this should be 4 watts. I squared R, this should be 4 watts. And I squared times R, 16 watts. Okay. Notice that the power from the battery should be I times E, which is 2 times 16, is 32 watts. 32 is the same as 8 plus 4 plus 4 plus 16. Okay, you get 16 plus 16. So the power being supplied by the battery is used up in all the resistors. Okay? So, Again, that's a nice way of checking. So all kinds of ways of checking this thing. And when you get, a little practice on these things, these simple things you can do in your head. Okay? So nothing to it. All right? Couple more things that I want to talk about. Okay? First, there's something called a ground. And there's a whole bunch of different symbols for a ground. This is the one that we're going to use. Okay? We're going to stick with this one for ground. Okay? Different people like different things. This is the one that we're going to use. What's a ground? When I've been writing down my loop rule, for instance, okay, I've written down that the sum of the changes in voltages through the loop is equal to 0. Okay? Well, when I got this, I'm talking about the changes in voltages. And so, for instance, if I've got some battery here of E, and I got some, delta VR here, some resistor here, then I know that whatever the voltage is at this point here, the voltage up here, let's call it some V0. Okay, whatever that voltage is, I don't know what it is. But the voltage after I go through here, up here, this is V0 plus E. Okay, the voltage has been increased there. And it's the same right here. It's still my V0 plus E here. But when I drop down, this V0 plus E minus delta VR. Okay, and if I want these two things to be equal, because I get back to the same spot here, then I know that this combination has got to equal 0. But this only says how much I change the voltage as I go across two different points, as I go across some sort of circuit element. It doesn't say anything at all about what the actual value of that voltage is. Okay? But notice, it all cancels off. The electric current doesn't depend on what this absolute voltage is at any point, and so you might say, I can ignore it. And this is true for every situation except for one little important point, which is what if you've got two circuits? Okay? Two circuits connected together, okay, maybe with some other batteries and things like that, all kind of talking to each other. So now you've got these things connected. And so you can have some E1 here, you can have some E2 here, and you can work out the same sorts of problems, the same sorts of things and so on. But now that they're talking to each other, the actual value of the voltage on one, if this is some V0 and this is some other V0 prime, some other change in voltage, well, if these two things aren't equal to each other, you're going to get currents flowing where you don't want them to. And so if you're hooking up a TV to a DVD player and things like that, well, maybe they're not at the same voltage. Maybe they've got a difference in voltage, so you get extra current flowing through. Maybe that's bad for your circuits. Okay? Maybe that blows something up. And so what you really want is that you want these two circuits to be at the same reference. Okay? You want these things to have the same sort of overall voltage. How do you do that? Well, you look on your plugs, okay, where you got one long side here, one shorter side, then you got this little thing down here on the plug. This is your ground. And what that does is it gives you this, if you open up the wiring, okay, you got 3 wires in there. One is black, okay, and that's not going to show up very nice here. One is a black wire with a little copper in there. Okay, so it's black sheathed with the copper. The other is white with a little, that's the sheathing with the copper. And then you got a bare copper, which is actually wrapped in paper. And these are the 3 different wires that run in most plugs. Sometimes you get more depending on what it is you want to do. Okay, this wire here is what's called the hot. Okay, this wire here is called the neutral. And then this one here is the ground. Okay? And the hot usually takes the current in and the neutral brings it back. And then the ground runs through the wiring in the house to your main panel. And then there's a bar, a big copper bar. At least this is one way of doing it. A big copper bar which is dug down into the ground. And you run another wire to this thing. And this essentially drains off extra charge, drains off extra voltage. And essentially what this thing does, this is your ground, this is this thing here. What this does is it defines V0 to be 0. We say anything that's connected to this ground, by definition, is at 0 volts. And so if you connect this part to ground and this part to ground by plugging them both into the same plugs, then you know that this side here is all at 0 volts and this side is at 0 volts, so there's no excess charge that's going to be transmitted from one to the next. Okay? And so under normal circumstances, this just defines a 0 voltage. It doesn't affect the circuit in any way other than that. Okay? I say under normal circumstances, well, if you get power spikes or something like that, excess energy can be drained away into the ground. And again, this is dug into the ground, okay, into the earth. It can drain off some extra energy, okay? And so that's the ground. And all that does is just define your 0 volts, okay? So for instance, just to show you, a real easy example, okay, suppose you've got 2 volts, 1 ohm, okay? And this thing here is grounded. Well, call this point A, point B, point C, and point D, okay? What's the voltage at A? What's the voltage at B? What's the voltage at C? And what's the voltage at D? Okay? Well, you know the voltage at B. That's easy. That's 0. Okay? You know the voltage at A. It's connected by the same wire, so that's also 0. Now, at point D, okay, what's that voltage? Well, it's been bumped up 0 plus the 2 volts, and so that should be up at 2 volts. Okay? And then the voltage at D. Okay, the voltage at D should be 0 plus the 2 volts. Okay, you increase when you go from A to D, you increase by the 2 volts. And so that should be 2 volts. Now the voltage at C should also be 2 volts because it's connected to D. Now when I go from C to B, then I have a change in voltage, delta VR, which is negative, and that should be minus the same E. Why? From the loop rule. And so that should be minus 2. And so the voltage at C should equal the voltage at B. Sorry, let me write it the other way. The voltage at B should equal the voltage at C minus 2 volts. And that should be 2 minus 2 equals 0. Okay? And so everything checks. Okay, and so that's the idea of a ground. Right? Hopefully this is making sense. Again, we're going to see better examples in the next lecture. The last thing I want to talk about is capacitors. Okay, capacitors in series and in parallel. Okay, so you can do the same thing with capacitors. And again, capacitors are useful for storing up charge. And suppose you need a 10 farad capacitor, but you don't have a 10 farad capacitor, but you got 2 5s. Okay, how can you connect those things together? Okay, could you do it in such a way that it's the same for resistors? Turns out no. Okay, turns out it's a little different. And so let me sort of take the case, okay, of capacitors. I started with series last time. Let's do parallel this time. In parallel. Okay. In this case, suppose that you've got some battery here, and you use that to charge up a capacitor, C here, okay, C1, but you've also got another capacitor over here, C2. And I want to say that this thing is equivalent to some E here, C equivalent. So in other words, if I choose the amounts correctly, this one capacitor does the same job as the 2 of these in parallel. Okay? So what do I have? Well, this this voltage is pushing out some charge. It's putting out some current, and that means that you build up some charge, say positive Q, on this top plate of the capacitor, and negative charge Q on the bottom capacitor. Okay, that's good. And so the change in voltage across that capacitor, okay, equivalent capacitor, is Q over C. It's the charge on the plate divided by C equivalent. Okay? So in other words, the Q here is equal to, is that the one I want to do? Q equals C delta V. Yeah, that's right. And so the Q should be C equivalent times delta V for this C equivalent. Now, remember, this is not IR. You don't have resistors here. This is something different. Okay? So this is the charge on that spot. Okay. Now I got to figure it out in terms of here. Now here's the idea. This battery is pushing out the same current, and so it's pushing out the same amount of charge. But because the current separates, the charge is also going to separate. The charge that you put on the capacitors is going to get split up. There's going to be some Q1 on this capacitor and some Q2 on this one, with a minus Q1 there and a minus Q2 there, in such a way that the total charge which comes in should be Q1 plus Q2. Okay? The total charge which is being produced by the battery is equal to the charge on plate 1 plus the charge on plate 2. Now, because there's charge on plate 1, Q1 should be equal to C1 delta V C1. And Q2 should be C2 delta V C2. Okay, just from this rule. Okay, just from the definition of the change in voltage through the capacitor. All right, so far so good. But by the loop rule, delta VC1 is equal to E, and delta VC2 is also equal to E. And in fact, over here also, delta VC equivalent is also equal to E. It's just one loop. Okay? And so, whatever voltage is supplied by the battery goes into charging up the capacitor. And so what do I find? That my Q should be equal to Q1 plus Q2, and Q should be C1 times delta V C1 plus C2 times delta V C2, but that's C1 E plus C2 E, and that's C1 plus C2 times E, and that should be Q. But from my equivalent capacitance, okay, in that case, I found that Q was equal to C equivalent times delta V C equivalent, which is also equal to E. And so this is C equivalent times E, but it's the same voltage in both cases. It's the same charge in both cases. So this tells me for capacitors in parallel, okay, capacitors in parallel, C equivalent is equal to C1 plus C2 plus however many you got. Okay, so capacitors in parallel, to get the equivalent capacitance of a bunch of capacitors in parallel, you sum the capacitances. Notice that is different, wherever it is, that's different than resistors in parallel. In the case of resistors in parallel, you take this inverse stuff. Resistors in series, just add. Wherever it is. Right here. So, resistors in series are like capacitors in parallel. Okay, so let me write that down. So, resistors. Okay, series. You write R equivalent is equal to R1 plus R2 plus however many you got. Okay, capacitors. Okay. Capacitors in parallel. C equivalent is equal to C1 plus C2 plus however many you got. Okay, so they're the opposite thing. Now, resistors in parallel. Okay, you get 1 over R1, R equivalent is equal to 1 over R1 plus 1 over R2 plus however many you got, 1 over R equivalent. Now, if nature was at all nice, capacitors in series would also be 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over Cn. Okay? Is nature nice in this case? Yes, it is. Okay? So series and parallel resistors and capacitors do the opposite things. Resistors in series are simple, capacitors in parallel are simple. Resistors in parallel are more complicated, capacitors in series are more complicated. Okay? And should I show you where it comes from? All right, what the heck? Okay? I'll do the same derivation. Okay? Just to show you where it comes from. By it, I mean capacitors in series. And this is where we'll finish off, okay? We'll save more complicated examples for next time, but we've got everything we need now, okay? So capacitors. Okay. Capacitors in series. So again, here's the same idea. I've got some E here, and I've got one capacitor C1, and I got another capacitor here, say C2. Just start with, just 2. Okay, but it generalizes. And I want to say that this thing here is equivalent to 1 E here and 1 C equivalent. Okay? So again, we worked this thing out before, and you know that the Q here, which comes from the electric field, the voltage rather, Q is C delta V times delta V capacitor. Okay, so I'm going to write it this way, delta V capacitor equivalent for this equivalent capacitor is Q over C equivalent. Okay, so again, same thing as we did before. Now I turn my attention to these ones in series. Okay? Now in this case, what's going to happen? Well, from the loop rule, I know, and I think you can probably see this by now, that E should be delta V C1 plus delta V C2. How do I do that? You just go around in a loop, okay? But I think you can probably see this by now. Okay, if you can't, you work it out. Now, what's the delta VC? Okay, well, this should be Q on 1 C1 plus Q2 C. I am so sorry, I did that wrong. Okay. Q equals C delta V, so this should be Q1 over C1 plus Q2 over C2, where I put a Q1 here and I put a Q2 there. Now, what happens? Is Q1 plus Q2 equal to Q? No, not in this case. Why? Here's what happens. Suppose that you've got your battery supplying some positive Q, and here's your first capacitor, and here's your second capacitor. This, the battery brings in charge Q, and it smears itself, that same positive Q, on the top surface of this first capacitor. And that induces a negative Q here, okay, on the other plate. It's the same amount. Okay, you're putting in this amount of charge. That's how much charge builds up on there. Now this wire here connecting these two, that started off neutral, but you just pulled a negative charge over here to the left plate. That leaves over a positive Q to the other plate, which then induces a negative Q. And so what that means is that the charge on the first plate is Q. The charge on the second plate is also Q. So the charge is the same in both cases. And so if I go back, that my E was equal to this Q1 over C1 plus Q2 over C2, well, that's just the same as Q over C1 plus Q over C2. And so this is the same as Q, 1 over C1 plus 1 over C2. Okay? So that's the electric field. And this would tell me how much capacitance or how much charge I put on each of these plates. But if I go back to my equivalent resistance, my delta V through this capacitor, which again has got to be E. It's got to be E because those are the only two voltages. For my equivalent things, I know that Q is equal to, E is equal to Q over C equivalent. And if it's the same E, and if it's the same Q, then that tells me that 1 over C equivalent is equal to 1 over C1 plus 1 over C2. Okay, so sure enough, capacitors in series act like resistors in parallel, and resistors in parallel act like capacitors in series. Invite whatever I said. Okay? They act opposite, equal and opposite. Okay? And so based on this, with these laws, you can work out all kinds of nice sorts of situations. Okay? And I'm tempted to do one more example. What the heck. And one more example, just to show you one more interesting situation. Okay? Again, just something real simple. Suppose you have another circuit here. Okay, so one more example. Okay, then we'll finish here. Suppose you got a battery like this, where you've got, 5 volts. Okay, just making up numbers. Suppose you've got a resistor here, and another resistor here, And let's suppose, I don't know, 2 ohms and 3 ohms. And suppose now you got another battery. And I'm going to put it in like this. Okay? And let's suppose that this is another 5 volts. Okay? So you got doubled up batteries. And what the heck, just for fun, throw in a ground. Doesn't do anything, okay? But just for fun. What's going to happen now? Now you got 2 batteries. And notice, this is your positive side, this is your positive side. As this battery pushes current out in this direction, this battery also pushes it off in the same direction. So in this case, okay, the current in this circuit, okay, should be 5 plus 5 over 2 plus 3. How did I get that? You figure it out. Okay, you figure it out. And so 2 amps. Okay, the current in this circuit should be 2 amps. Okay, and so the current through the entire circuit is 2 amps. It's all the same. And you can figure out all the powers and all that kind of stuff. It's good practice. But what if you had something a little different? Okay, 5 volts, 2 ohms, 3 ohms, and 5 volts. Well, now here you got a positive here pushing in this direction, but your positive puts it in that way. You've put the battery in backwards, in other words. In this case, I should be 5 minus 5 over 2 plus 3 equals 0. Why is that? Well, you're pushing in the wrong direction. Remember, I talked about how you got to bump up in voltage when you're moving in the same direction as the current. The current's going this way. Here, you're fighting that. Here, this pushes back. So, because this second battery is pushing back, it's costing energy. It's draining energy away from those charges. And so you lose voltage when you go in that direction. Okay? That's the idea. What if it was 6 volts and 5 volts? Well, it'd be 6 minus 5. You'd have 1. And so the current would just kind of trickle. Okay? That's the idea. Okay? And so this introduces the basic ideas of circuits and things like that. Okay? And the important things to remember are these Kirchhoff's laws, which are generally true. Okay? They're going to be true for DC circuits. They're also going to be true for AC circuits when we talk about those things. Okay? So these are important. Remembering the delta V resistor is I times R. Delta V capacitor is Q over C. And delta V battery is this E. Those are important. And what that P is equal to I times delta V. That's important. And then these ideas for series and parallel circuit elements. Okay? All very, very useful sorts of stuff. Okay? Incidentally, there's plenty of other ways of working these things out. Again, if you take circuits or have taken circuits in electrical engineering, you can work things out in terms of matrices and determinants and all kinds of other tricks and all kinds of other fancy things. I'm just showing you a way of working it out. Okay? And there's plenty of ways because it's just algebra. It's just solving systems of equations, and that's really all it is. Okay, so whichever way you like best, use that. But this is, kind of a nice way. Okay, nice way. I mean, break up a circuit into these equivalent circuits. Okay, like we did here. Break it up into sort of an equivalent circuit, and then figure things out from there. Okay, this is much nicer, I think, than writing a system of 5 equations and 5 unknowns. Okay, this one you can do in your head. Okay. So, spend a little time looking at these things, okay, work the worksheet problems and so on. Next time we'll talk about more sophisticated things involving switches and other kinds of systems, okay? See you next time.